Welcome back to the Ephemeris podcast. I am your host, Aphelion, and hopefully y'all are doing amazing. Um, a very crazy and stressful week is now behind me because it was the week that I participated in regionals, and I got third in astronomy. I was pretty buzzing about it at the time I was writing because I was writing the script for this podcast when the results were coming out, and I was ecstatic. I was buzzing. I did not expect to do that well, but yeah, pulled it through, pulled it off. The test was meticulous. It was more mathematics heavy, and I believe, or from my experience, I was only able to really answer 50% of the questions that they gave us, but it turns out that that was enough to get third, so I'm still happy about that. It's a dub nonetheless. In terms of some of my other events that I did, because I didn't just do astronomy, I did not medal, but I got top 10 finishes in the other two, so still a dub nonetheless. Regionals as a whole, very big W. We're going to states. I'm happy about that. More time to really train my astronomy brain. It's a bit cringe, but yeah, that's behind us now. So we're going to get into the topic of today's podcast, which is FUor Orionis Stars. And I know, I promised to talk about luminous blue variables and all that jazz, but that's another one of those extensive research videos that I don't think I'm going to be able to pull off this week. So I decided to take a little bit more of an extended break from those kind of episodes, because it's not that I'm trying to be lazy. It's that I like genuinely enjoy doing those extensive research episodes, but I don't want to give up the streak of the podcast just because I'm not able to do those videos, because the one thing I highlighted when I started the podcast was consistency. I wanted to keep it going so that it didn't fall off after, a couple of months. So I'm doing these episodes to make sure I can keep a little bit of consistency for this podcast so that when we get to the extensive stuff, it's going to be really enjoyable. So anyways, FU Orionis Stars. They're a pretty recent finding for me. I just figured out about this, somewhere along the road of studying for astronomy, and I want to investigate it. So that's what we're going to do today. So what are they? They're a type of pre-main sequence star other than T-Tauri variables and Herbig-Haro objects. So there's three pre-main sequence stars that we know of that are more popular or more well-known, I should say. And that's T-Tauri variables, Herbig-Haro objects, and then FUor Orionis Stars. So we're going to talk about FUor Orionis Stars. And I think I might call them FUors by the end of this podcast, because it's going to be kind of a long name. But anyways, in general, what we imagine main sequence stars to be are stars with an accretion disk and interstellar cloud around them. And if we think about why this might be the case in terms of stellar evolution, it makes sense, because a star is forming through gravitational forces. It's in the process of accreting matter to make that main sequence star, on top of what it already has, around it, like the interstellar medium surrounding it. And you have kind of this in between the actual star and the interstellar medium that is your accretion disk, right? So that all kind of fits into some of our intuition in terms of stars. And it should be noted that stars like FUors are phases in the protostar stage where the star begins to let go of its accretion disk, and you can imagine that as sort of the star losing its training wheels, really getting into that. Would you call it an adult life? I don't know. You could. But what is special about FUors is they go through extreme magnitude and spectral changes in this phase. A little bit of instability in the mix before they get onto their stable life. And let's just refer to them as eruptions. These eruptions usually occur in the span of a year, and after FUors reach maximum luminosity, they tend to stay there for a while and gradually decrease over the span of multiple years. And I mean, if you were to draw a connection to that description with what you see in Type 1a supernovas, I guess you could make that little bit of a connection because supernovas kind of do that when you look at the luminosity graph. But I'm sure there's some difference between the decrease in luminosity after the big spike that kind of differentiates it from supernovas. So just a little tangent. The phase of a star is said to last for a couple of decades, and we've never really seen one of these stars kind of completely shut off and stop, get to that really low point in luminosity. So what we do suspect is young stars will go through 20 eruptions in its lifetime before it gets to that main sequence. A lot of what we detect from FUors come from the accretion disk that surround it. We get a F to G spectral reading on the inside and a K to M spectral reading on the outside of the disk. So that tells us a lot. And just a side note, it's kind of cool, like the accretion disk being in the mix of FUors because there's some similarities it has to cataclysmic variables and symbiotic binaries. But it's not completely significant because we can't dive any deeper into that and say, oh, there's a connection between these two. There's some differences that I will go over in a moment that'll kind of give reason to why, that connection is a little bit insignificant. Okay, so given all of this, how do we explain the eruptions of FUors and similar pre-main sequence stars in general? Because we got to get an explanation in on this podcast. That's what we do. Well, according to studies, thermal instabilities tend to be the instigator of outbursts near the disk of the star. So a bunch of heat that's being created by these eruptions makes the matter really ionized, which is very common for variable stars. I don't think I've discussed this before, but the explanation to the variability of like Cepheids tends to involve a lot of the ionization of the elements that the star has. So that's there, right? But once that matter joins the rest of the star, the eruption declines and the present hydrogen can recombine because, it's cooled down a little bit. It's not too hot and mumbly jumbly up in there. And these eruptions are signaled by critical points in the mass of the accretion disk. So as I was mentioning, right, the stars tend to accumulate a lot of mass with these eruptions. So kind of looking into that aspect of the star will really, really help us. And so the scale of the eruptions really depends on how fast the matter is being integrated to the star, because again, that's something that has to do with the mass of the whole system. So a study led by S.J. Kenyon confirms this model, it not only accounts for the increase in luminosity, but it explains the broad spectral energy distributions, the variation of rotational velocity and spectral typhoid wavelength, as well as other properties that are commonly observed with these kind of stars. But there is something that is missed out with this whole theory. It's the fact that FUors actually flicker. And what I mean by flicker is that they have minor visible fluctuations that no other pre-main sequence stars have. And when they did this study, they tried to compensate for that by looking at other stars that may like you can make a case for there being flickering in those, but they just weren't able to kind of put those two together. And so FUors, they're flickering, if we were to put it into like kind of a little bit of a more statistical analysis, they tend to be 0.1 to 1 magnitude. And, they're little flickers. What else can I say? The study I just mentioned, right, S.J. Kenyon and all, upon finding this unique feature, they tried to find it, but it was a minute detail that justified creating distinctions, because if we don't make that distinction, then it's very easy for us to just say Orionis is a part of the T-Tauri stage. The only difference between the two would be the magnitude if we don't consider the fluctuations, where, T-Tauris tend to be, I think, 1 to 3 magnitude, and Orionis tends to be bigger, just 3 to 6, right? And the theory also used to be that Orionis stars were nova, because if we go back to the fact that their accretion disks have similarities to cataclysmic variables, you can draw that conclusion too. You can make that theory up too, but there is those little flickers give justification for distinguishing them. And some other heavier implications is because FUorionis stars, or FUorionis as a star and not actually the type of star, because it's so young in its stellar life, it could be helpful for understanding the development of solar systems based on chemical changes to the star that happen, among other things, and how that affects planets, which we've talked about the Fulton Gap before and exoplanets and kind of what's leading the chase in terms of what we want to discover. And maybe, FUorionis stars are really going to help put some of that, or, FUorionis stars can be in the mix of that whole saga. So that is all I have for today's episode. If you guys are listening to the podcast, I appreciate it. I appreciate you kind of listening through some of the less intensive episodes because, the extensive research episodes that I do, they're able to get clipped more. They're more like enjoyable parts of the podcast to listen to, but I needed my breather, and I thought this would be really nice for the consistency. So if you're listening, I genuinely do appreciate you guys sticking with me through all of these episodes, no matter how crazy or not crazy they get. If you're listening on Spotify, I would sincerely enjoy a follow or appreciate a follow. And if you're listening on YouTube, a subscribe would help out the channel a lot. And until next time, I will see you guys later. Peace.